All right, and problem 109, part B, sub 2. All right, so now we're going to find the tension in string 2. Now look, here's what I want you to see. 109, B, part 2, tension T2. All right, so now there's two different ways we can approach this. We have, if we use M2 up here, we have T2, which is unknown, and T1, which is now known, right? And those are the forces acting on it in the direction of acceleration. You know, we can do this right here. We got normal force and mg, and oh yeah, I forgot about friction. Yeah, there's 5 forces. That's a pain. Let's think about what's happening on the other end of T2. What's going on there? All right, we got. Oh, I put the blue marker. All right, so now we have M3 here. We have T2 acting up and M3G acting downward. Which one do you want to evaluate?
Right.
Yeah, the correct one, which is the one on the right. All right. So now that we've done that, it's just going to be the elementary equation again, but with an important difference. When we plug in A, it's going to be negative. Yes, because if this is positive, we know acceleration is downward. Okay, and we have T2 minus M3G, which is what we get the elevator equation from. That inherently means then up is positive, right? Because if we say T2 minus this, right? We could turn the system upside down and say downward is positive, but then we get T2, then we get M3 times the quantity G minus A. We put in a positive acceleration. Either way, we're going to have a parenthetical expression. This right here, G blah 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 part is going to be less than A. It's less than G. Okay? Because the tension has got to be less than M3G, doesn't it? How do we know that? It's accelerating downward. So the net force must be downward, so M3G here must be bigger than T2 acting upward. All right, let's just get to it though. Net force is equal to M3A. Again, that's an A that we know. That's an acceleration we know. Net force is equal to T2 acting in the upward positive direction minus M3G, the weight, acting the other way. So now we go blah, blah, blah. You guys know the whole thing. We can just get to the point, and that's T2 is equal to M3 times the quantity G plus A. Okay? So now we just plug in the numbers that we know. T2 we don't know. That's what we're looking for. M3, 25 kilograms. G, 9.8 meters per second squared. A is, right, negative 0.6 meters per second squared. All right? You could do that, or you could just say minus in there. We know what we mean, right? Sure. All right? So now, 9.8 minus 0.6 gives us 9.2. 9.2 times 25, 196 plus 49, 245. Somebody help me. Pausing. Wrong. 230 kilogram meters per second squared. Newtons. All right. My mental math went astray. All right. T2 is 230 newtons. I said that they would or would not be equal. What did you guys, did anybody think that those those tensions on either side would be the same? Okay. Can we think of a logical construct, a logical explanation as to why that couldn't possibly be true? Let's just take a look at that. That's a worthy diversion. All right? Think about the forces that are acting on block M2. All right? What do we have? Block 2. We're just going to take the surface of the table here. We're going to put block 2 on it. Here it is. You can tell it's block 2 because I call it M2. All right, now, think about this. If the tensions on either side were equal, why would it accelerate? It wouldn't. It would not accelerate. All right, and one of the clues, look at the problem, if you will. There's a clue that says that this thing is going to move. What is the clue that says this is going to move? Object moves, okay? Well, a more subtle clue, I didn't realize it said that. Something about coefficient of friction. Kinetic friction, the coefficient of kinetic friction tells us that it is going to move. All right, so now, as a challenge problem, and I'm going to actually ask you guys to do this, and then we'll go over it in a second rather than do another problem, is what is the minimum coefficient of static friction that would keep the system from moving if it was released from rest? Okay? So in other words, you're going to have somebody on either side, and they say ready, set, go, and they let go of their respective masses, M1 and M3, and it doesn't go anywhere. How are you going to find that out? All right, we'll come back to that in a second. All right, so we're solving for an extension of problem 109. We'll call it 109 extension. That's what we're doing. All right, so what we're saying is, what is the minimum coefficient of static friction that we could have between M2 and the tabletop right here? That doesn't show up very well. And the tabletop right there, so that it would keep it still if it was released from rest. Keep the system still if it was released from rest. And what we came up with was, here's our system again, with fancy M in it, okay? And we have in this direction acting M3G, and in this direction we have M1G and friction, right? In this case, static friction. Is everybody okay with that sort of blobby free body diagram? Yeah. Okay, friction's acting again on mass 2, so that friction is going to be mu times M2G. So if this is released from rest and does not go anywhere, then we know that it's in equilibrium. It's in static equilibrium. The net force is equal to 0. So net force is equal to 0. Net force is same expression as before. M3G minus M1G plus friction. In this case, static friction. Okay? All right, so if those two, we got like that, and that's equal to 0, and that funny box happens. All right, so we just know then that M3G is equal to M1G plus static friction. Whoa, that is not an F. That was a squiggle. Static friction. And static friction is going to be equal to M3G minus M1G. And since static friction is going to be equal to mu static times the normal force acting on block 2, which we already decided is just M2G, we get this right here. And since we like clean equations when we can get them, let's just cancel G's out. They come across everything, right? So the answer would be the same on Mars, or the Moon, or Jupiter, but not Saturn. I don't know why. Saturn's weird. All right, so mu static is equal to, check it out, M3 minus M1 over M2. All right, and this is what we did in our heads a few minutes ago, right? The difference between them is 15 kilograms, all right, because M3 is 25 kilograms minus 10 kilograms gives us 15 kilograms divided by 80 kilograms. Look at this. All the kilograms go away too, so we could be measuring in grams or any mass, slugs, any mass unit. 15 divided by 80 is 0.1825. What are the units for coefficients of friction? There are none. It's dimensionless. So mu static, 0.1825. That is the minimum it could be, because remember, mu static times normal force is static friction, the maximum that it can be, right? So that's the most friction we can get to meet the minimum requirement. Right? Again. Right? I'm going to go ahead and stop the recording, and we can just scan this.